This is a retrofit information support and expertise event funded by Department for Energy Security and Net Zero. Today we are proud to have Dr. Martin Fletcher, who's a senior research fellow at the Leeds Sustainability Institute, who's going to be taking the masterclass today. So thank you so much for joining us today, and over to him.
Great, thank you. Yeah, so as mentioned, the meeting today is really about the deterioration of retrofit. And it centres on a project that was funded by the Department of Energy Security and Net Zero as well, really looking at the role that deterioration of insulation products has in our retrofit buildings. So we'll start with a really brief overview of the research group that I'm part of here at Leeds Beckett University, and then the challenge that we're kind of addressing with this research and the project that we're talking about. And then we'll get into the findings themselves and how they can be taken forward and usefully applied. So first, a few words about myself. So I'm a senior research fellow here at Leeds Beckett University in the Leeds Sustainability Institute. And my personal expertise is in monitoring and evaluation of occupied buildings. So I do a lot of work with energy use before and after a retrofit and looking at occupant perspectives as well. And I'm the principal investigator on this piece of work we're talking about today. So that's why I'm the one speaking. But as everyone knows, I'm sure, it takes a great team to produce great research. So I'm part of the Leeds Sustainability Institute. And there's a group of us with the research sitting in three broad themes. So first of all, we look at the behaviour of people and working to understand why people behave the way they do. So how they use energy, the choices they make to do with energy, and then how they interact with their kind of socio-technical surroundings, so their operation of their heating systems and their purchasing behaviours. The lion's share of our work's buildings. So we do a lot of work covering everything from design reviews, dynamic thermal simulations, through to building performance evaluation, forensic testing and monitoring of buildings before and after retrofit. And then finally, we do research in urban environments. So that's more considering the context of the buildings. So where they're sat, the green space around them, urban heat island effects, that kind of thing. So while we do have these three themes, it's not a siloed approach, which is really, really helpful because it gives us this ability to apply these different skills and knowledge and research methods to the work that we do. So that's briefly the Leeds Sustainability Institute. Please do reach out to me after this presentation if you've got any questions about the work that we do outside of this project. But today, we're talking about the Deterioration of Retrofit Insulation project, or I'm going to call it the DRIP project. That's the handy acronym that we came up with. But first of all, why are we doing what we're doing in the first place? So domestic dwellings, and I'm sure many of you in the room already know this, but they account for around about a fifth of UK carbon emissions. And the majority of this is associated with space heating demand. So to reduce this heating demand, it's absolutely essential if we need to meet our national and international net zero targets for emissions. And insulation for new buildings and existing buildings through retrofit is absolutely critical. But it's important for several reasons. So there's the efficiency aspect. So insulation reducing the amount of energy that you need to heat and cool a building, and that then leads to lower energy bills, but also reduced emissions. But also insulation can be really impactful on comfort and well-being in a space. So improving insulation helps to maintain a constant internal temperature that enhances thermal comfort. And it can also offset things like mold and damp risk. And also, finally, the environmental impact again. So coming back to those big picture national and international targets to reduce our impact on the environment, insulation lowers those greenhouse gas emissions through lower energy expenditure to heat our homes. And that all supports our sustainability goals. But although national retrofit programs and insulation programs generally have had an incredibly significant positive contribution towards reducing domestic heat demand, there is uncertainty around how long we can expect to see these benefits. So our current narratives around retrofit and insulation generally make a few assumptions. So they assume that the retrofit's done correctly and to a high standard. They assume that materials themselves will remain in good condition throughout their service life. And they assume that the energy saving that we have through installing insulation is going to be consistent throughout that product's lifespan. So the DRIP project, funded by DESNZ, Department of Energy Security Net Zero, it aims to evaluate these assumptions, and starting by evaluating the state of the art for insulation deterioration research. So what do we already know about this phenomenon? So the project was designed as a phase 1 evidence gathering exercise. with the aim to establish our current state of knowledge on retrofit, degradation, or deterioration. And we set out several research questions to do this. So first of all, we want to know what's the current level of knowledge on how long these products last and how they deteriorate over time. How can poor quality retrofit be classified and evaluated? So if we think there's a problem, how do we even classify that and compare one problem with another? What sort of insights can retrofit degradation provide, and what kind of existing data sets do we have that can do that for us? So we've got a lot of big data sets out there currently. Can we get new knowledge from old data? And what sort of methods are appropriate for evaluating deterioration and change over time? And if we wanted to roll this into a second phase to go and get more data, what sort of sample would we need to get to be representative for the UK? Now, that's quite a massive scope. So to be achievable, we're limited it a little bit. We're limited to a UK focus because it's most relevant to our own kind of policy goals. And we only considered solid wall insulation products, external and internal, cavity wall insulation products, so mainly filled, and loft insulation products, as these are the most dominant insulation types in the UK. And by establishing this existing knowledge, we can then understand the scale of the problem, and we can start to produce recommendations to fill those gaps in our knowledge. So we designed this around 3 key activities. First of all, a wide-ranging and systematic literature review. So this was to encompass the academic literature and also any grey literature, so technical reports, industry literature, third-party literature. Second, we looked at what technical analysis we could do on existing data sets. So primarily thinking about the National Energy Efficiency Data Framework, or the NEED data set. What could we do with that to learn a bit more about change over time? And finally, we almost jumped ahead to the answer and realized that there were going to be a few gaps emerging as we did this process. So let's talk to some experts as well. Let's try and capture knowledge that's locked up inside people's brains, essentially, that isn't published and isn't publicly accessible, but it's still valuable to capture. And from that, we can develop recommendations and guidance for next steps to consider the problem of performance change over time. So starting with the literature review, what do we know? What do we know? So when considering the deterioration of insulation, what we're trying to do here is define change in performance after it's been installed. So we started thinking retrofit, but really these do apply to new build as well. It's all just change from the point of installation. So this could be due to the quality of the initial install. So if you install it badly to start with, this can lead to gaps, thermal bridging. These can all reduce the effectiveness of the insulation, and they can actually accelerate the decline in its performance as well. We're thinking about wear and tear. So this is a big one. This is interaction with humans and the natural environment that disturbs that insulation after it's been installed. So this could be accidental, or it can be intentional, but with an unintended consequence. So for example, if you're trying to access your top floor ceiling from above to change a light fitting, you're going to possibly disturb the insulation in that loft accidentally, or intentionally. You might actually make a change and make it better or worse, but it's changed from its original condition. And finally, material change. So over time, this is just the natural change in a material. So this could be to do with moisture accumulation, but it could also be loose material settling under gravity. It could be loss of blowing agents, all sorts of changes to the material properties themselves that are otherwise unavoidable. And it's important to note at this moment that this isn't the performance gap. So the performance gap is probably something that many people are familiar with. This is the performance gap thinks about the difference between the design intent of insulation and its reality on the first day, on day one. That's not what we're looking at here. For deterioration, we're looking at performance decline. So however it was installed on day one, that's its 100% potential. And then how does it get worse from that point onwards? Now, if you install an insulation product poorly to start with, you can accelerate that deterioration, the pace at which it changes negatively. But we're not looking at a comparison with perfection. We're not looking at a perfect install versus an imperfect install necessarily. So first of all, the academic peer review literature we covered. So let's think about, first of all, where did that data come from and how representative was it? And the majority of research that's out there in the published literature is either simulation or lab-based, and there's a real lack of real-world testing of materials, presumably because it's a fair bit easier to simulate and model or extract and test back at the lab than test in the field, and we'll discuss that a bit later. But this does come with an issue because The simulations that are used to project the performance of insulation products over time rely on multiple assumptions that aren't always fit for every context. So we have uncertainty around the material properties and the homogeneity of the system. And these can all lead to stark differences when we compare what we modeled an insulation product to do over time versus what we measure. Similarly, laboratory studies, they have to almost simulate aging. They have to force that aging process. So they use accelerated aging methods like vibration plates to settle loose materials. They use extreme heating, extreme cooling, extreme wetting. And none of these are truly representative of the gradual process of aging out in the field. So more often than not, it's a slow accumulation of moisture in a material, not a sudden downpour that soaks it through. More often than not, sometimes you do get leaks. When we're looking at testing thicker solid products like an expanded polystyrene board, these, to test them effectively, focus on thin slicing of materials, which is going to overestimate surface effects and neglect the bulk material properties as well. So all that's to say that the laboratory tests, whilst useful, aren't necessarily representative of all materials in all contexts out in the field. The only way you can really do that is by testing a naturally aged product from a field environment. And where this was done, this was often, again, idealized or non-representative. So samples were taken from real contexts, but they were from non-domestic buildings, or they were from settings that were perfect, for want of a better word, so that lacking moisture ingress, lacking weather effects, lacking disturbance, really kind of biasing the data from real world examples. And we only actually found 5 of the studies that were based from the UK themselves. So a lot of excellent work happening over in Europe, but that's different construction types, different weather patterns. So again, we're starting to infer our own findings for the UK against environments that aren't UK relevant. So all that's to summarize is that the peer-reviewed published research on retrofit deterioration isn't comprehensive. It doesn't cover all material types or retrofit systems. And interestingly, one of the lowest represented insulation systems was loose materials that are used in lofts and cavity walls, which represents a significant majority of the domestic insulation materials in the UK. So some great insights that we'll talk about a bit further from that literature, but really lacking in the incomplete coverage. We also looked at grey literature sources. So these are documents that are reputable and useful, but they haven't necessarily undergone peer review. So that's documents from industry, from government reports and associated third parties. And there's varying levels of review that's taken place for those documents. So you need to have a bit more caution when interpreting them. And much of the literature from insulation manufacturers and associations suggested that insulation doesn't deteriorate, with product lifetimes limited only by the buildings themselves. Now, when we actually evaluated marketing materials, it was common for the same organizations to claim that competitor products did deteriorate. So there was a bit of a bias in those documents with unclear methods, sometimes anecdotal findings and unrepresentative settings. So whilst useful, it was pinch of salt on those documents. And interestingly, a lot of things were taken out of context from international standard, where the standards themselves often state that the thermal conductivity of products doesn't deteriorate. But this is under strict contextual settings that don't allow for moisture ingress, don't allow for compressive creep, which is the settling of loose materials due to gravity. So naturally, it would be wrong to assume that these strict lab-based conditions that are tested for international standard purposes are actually ever realized when a product's put in someone's loft in the real world. There's several good reports by third parties and government. The issue with these reports for the DRIP project is the scope of them. So they're often either too broad or too narrow. So they're either considering a whole house performance in a specific setting, not insulation types, or they're using national level data sets to infer statistical change. So using things like the NEED data set. So although they're really useful, you can't draw causative links between performance change as the way we'd like to for the aims of DRIP. So for example, something changing in a house to that insulation product manifesting into a change in its performance. So to summarize the landscape of the literature that we have on deterioration of retrofit, the research shows that many insulation, and if not most, if not all products, can see a decrease in the thermal resistance over time due to material change, due to wear and tear, and due to actual failure of the system itself. if it's been poorly specified, leading to accelerated performance change. But the main takeaway from it really is that the existing evaluation is not comprehensive at all. So there's unequal representation of products. There's certainly no clear winners or losers between different product types or retrofit systems when we look at the continuation of performance over time. And the tests that do exist are often not applicable to real-world contexts, so they're lab or simulation, and that goes doubly so for UK context as well. So the little information out there that is taken from real-world environments wasn't from a UK weather system or a housing archetype in the UK. So this uncertainty in the literature left us with a few challenges and a few next steps to capture more expert information. So we needed to start to shed some more light on the challenge of deterioration. And if we are to go forward and get some more data on this, how do we start? How do we tackle that knowledge gap? So we conducted 2 stakeholder events as part of the project, one after the other. So our first was an expert workshop with 20 industry professionals. And these were made up from professionals from the retrofit supply side. So that's insulation manufacturers, that's builders, retrofit designers, from the retrofit demand side. So the social housing teams and housing estate teams, and then also third-party construction professionals too. So building surveyors, regulatory bodies, insurance providers, trade associations, and expert witnesses, all meeting together in a World Cafe roundtable method. So in this method, we basically take the experts and split them into groups to mix up their expertise. So you don't just have one group of surveyors, one group of manufacturers, etc. You have a mixed group of expertise, and then these groups rotate around 4 different rooms, and each room is focused on an insulation type. So loft, cavity, internal and external wall insulation. And inside that room, the facilitator for that room guides them through a discussion around that deterioration of that insulation type with lots of pictures. And they'll talk it amongst themselves as a group and outline the issues they're observing and start to classify the insulation degradation. So this then led into the second activity. Once we've got a classification of the way that insulation deteriorates, we did a Delphi survey, which is a way of gaining consensus across a panel of experts on a given topic. So remember, we're trying to think what would a future data gathering exercise to give us more UK relevant and contextual information on retrofit deterioration look like. So we've classified the causes and consequences. Now, how should we measure and grade that deterioration, and what would a survey look like moving forward? So with the Delphi method, it starts with a questionnaire that's sent to the experts, and then anonymously they'll rate a series of statements, and it's all around gaining consensus. The researchers look at the responses, take forward the statements that are in agreement with one another, disregard the ones that aren't, and if you repeat that over several rounds, you start to agree a consensus approach for things like a measurement system, a grading system, and a national survey approach. Okay. So starting with the classifications that we got from the expert workshop, how did that shake out? What was the expert view on how we classified degradation of insulation? So for loft insulation products, started with a poor design leading to damage. So that's if, for example, you have a photovoltaic, a solar system inverter in the loft, but you don't provide any access to it, and you've got to crawl across that insulation to get there, that's going to be one of the reasons that you start to see damage. Blocked ventilation is another design issue. So if you shove it right into the eaves and you block up any ventilation to the space, you're going to accelerate that deterioration through lack of ventilation and moisture accumulation. Disturbance by humans or animals, that's a classic one, throwing the Christmas tree on top of it. And also damage from weather, water, debris. These are more of an accidental environmental consequence, so a slip tile in the roof letting water in. For cavity wall insulation, for older materials, a deterioration of the composition over time. So not so much a problem with modern materials, but older materials, the binding agents often saw a change over time, and that can often be twinned with the second point, the poor installation, so slumping or movement. If it's a partial fill cavity, the mechanical fixings or the fixings holding it to the cavity in a leaf coming away, and they kind of drop across in the cavity. And then also just general damage from ingress of water or weather or debris. The expert's point it is for internal wall insulation. Again, product or system design being wrong for the property. really, really challenging with solid wall homes, typically older construction, often have to be really careful in terms of ventilation and considering the moisture effects and whether that wall needs to be vapor permeable, the materials need to be vapor permeable to avoid unintended consequences. Not preparing that surface correctly as well. Again, bad system design and post-installation damage. So people interfering with the installation after it's been constructed. And external wall insulation. So for classifying this degradation, quite similar to internal wall, it's really not thinking about what the materials you're using and how you're using them. So a bad system and then bad maintenance as well and fixing. So with external wall insulation, we do see issues with maintenance of fixings, sealants and penetrations, all just allowing water to get behind that insulation product, accelerating its performance decline. And of course, damage from DIY and weather as well. So generally, we start to see broad themes emerging from these classifications, really. So the first are the mistakes that are made at the point of the retrofit or the installation of the insulation by picking a poor system with a poor design that ultimately leads to disturbance and issues later down the line. A lack of maintenance to the building. So rather than being proactive in the maintenance, being reactive, and often the damage has been done to the insulation product of that type. And then damage as well. So humans, animals, and weather is always a risk factor. And interestingly, in classifying these degradation issues, there was much less focus on the materials naturally aging themselves. So that's more of a secondary issue to the impact of external actors on the insulation products themselves. So we took this forward to the Delphi study to see how deterioration might be graded and measured. So if we're saying that the products are deteriorating, how would we go about comparing one with another to measure it and then grade it? So measurement methods, and thinking we would roll this out to a more of a larger sample. So it can't be, we're not looking at highly detailed case studies going into the minutiae of one property. This is looking at a much larger cohort of homes. So what kind of measurements could we do? So visual inspection, the first and obvious one. And there's two elements to this. It's looking at the percentage and the severity of that deterioration. So for example, a suitcase, sure, I've done some loft insulation, is quite a small issue in terms of energy consumption for the home, but quite a severe issue if it leads to a cold spot on the ceiling below that allows moisture to form, that allows mold to grow. However, a whole loft overboarded that compresses the insulation up there by 100 mil, now that's going to have a big impact on the energy consumption of the home, but probably a very little impact. There's probably not going to be any noticeable impact when you're inside that home because all of that compression is spread out over a much wider surface area. So you'll feel the impact in your bills and your carbon consumption, but not in a more visual way. So grading that against the percentage, but also the severity on the visual inspection. Thermal imaging, fantastic tool to see hidden issues, if you like. So using thermal imaging, we can look at seeing compression insulation. We can look at clumping inside cavities, identify moisture striking into and behind insulation products. So a really good measurement tool. Depth measurements in multiple locations, critical thing. So this isn't sticking your head in the loft hatch and just taking one measurement. It's looking at multiple places. Similarly, internal and external wall insulation. Are there bits that are cut out and missed and around? Are there areas where it's thinner because you had to make it thinner so that a door could open or a window could open? Because all of these things are going to affect performance and sometimes they can accelerate that deterioration process. And then borescope surveys again, just to kind of get access to areas that you can't see just by looking with the naked eye. And the Delphi study also revealed several risk factors when we're looking at if we're going to target specific areas for a future data gathering exercise. What are the areas that might increase the likelihood of deterioration of insulation? So converted or extended homes, anytime you change the original structure, there is a risk that you introduce additional deterioration to those products because you start to make changes, you interfere with that originally designed system. Exposed areas, flood risk locations, quite an obvious one. If it's a coastal area, a lot of driving wind, driving rain, anywhere with more extreme weather, it's going to affect the building fabric. So it doesn't have to necessarily be hitting the insulation product itself. But if, for example, it's more likely that you'll be getting issues with the tiles on your roof, for example, because it's a high wind area, that water will get in and affect the insulation that was concealed. Poor maintenance of homes is a big risk factor. Touched on that before, but by being reactive rather than proactive in maintenance is going to increase the risk of degradation, because if you wait until a problem has happened, then it doesn't, unless you take out the damaged insulation product and replace it, for example, then that product is going to be changed forever and that deterioration will be reduced, even if you replace the slip tile later. High occupancy homes, simply because there's more experience with wear and tear on any product, more people in a smaller space, and older homes as well. So thinking if homes have no roof felt, or if they have unusual building materials, they're more likely to present a risk of deterioration for insulation products, particularly where it's a retrofit. So where that home was never designed to be insulated, if you then insulate it, you need to be really careful that you use the right materials, and it's done in such a way that you manage any moisture or ventilation risks. So that's the landscape of the literature that's out there currently. But what did we learn from that evidence and from our expert stakeholder engagement? At this point, we're really thinking about how we can apply these learnings to mitigate the negative effects of retrofit deterioration. So to ensure the long-term effectiveness of retrofit insulation and minimize that deterioration effect, there were several strategies that emerged from the data that can be implemented. So the first is high quality installation. So you want to be making sure that you're using professional installers and installation systems, prepare the surfaces and do any remediation work before you try and retrofit or do any insulation, and avoid any gaps, any thermal bridges. Use the wealth of fantastic information from PAS 2035, Sustainable Traditional Building Alliance. You've got all these wonderful resources out there to do the jobs properly. It's making sure that they are done properly, because if the retrofit's done to a high standard initially, it really offsets a lot of the risk of down the line deterioration. Materials, another huge and very important factor. They are very different, and using the appropriate materials that are durable and compatible with the home that you're insulating will massively reduce the risk of deterioration down the line again. Specifically thinking moisture here. If you're retrofitting older buildings and solid wall buildings, they're much more at risk. To reduce deterioration of the retrofit performance, maintenance should be proactive, not reactive. So setting up routine inspections, maintaining ventilation systems, especially when they're not just fit and forget. So cleaning air bricks and making sure vents are clear is fantastic. But it often gets overlooked that a lot of fans and mechanical systems need filter changes. They need to make sure that they're still operating. They get clogged up as well, that they're still operating well. Maintaining that supporting system and maintaining the home generally will reduce the rate at which any insulation product's performance deteriorates. Considering the environment whenever you're choosing an insulation system. So things like weatherproofing. If you're confident that you can insulate a cavity wall in a high or in a more extreme weather environment with wind-driven rain, using the correct weatherproofing and being very careful that you use a product that's appropriate to the local climate. Design and specification kind of comes alongside quality installation. But yeah, getting your design right and detailing all of the complexity. So this is really, really important when you look at the big funding schemes for retrofit on, for example, large cohorts of social homes. Often a retrofit design will be specified based on an example home, but every single home is different. Every single one. It doesn't matter if it's a different occupancy profile, if it's got a lean-to garage at the back, if it's got a bike shed to the front, etc., etc. Every single home will be ever so slightly different. So do have a think about the design and specification of a retrofit installation for each home individually before you start doing the work. Because again, looking through the lens of performance change over time, you will mitigate a lot of that risk if you do it right first. And then monitoring and evaluation. So by monitoring the performance and capturing data, ideally before you even do anything to the home, and then certainly afterwards, you can track that performance change too. So rather than having to rely on assumptions of change, you can actually measure and monitor to see what changes over time. So The final thing really to ask, and it's one that as academics we always ask of every research activity, it's the kind of dreaded so what and who cares. So to put it another way, what are the implications of this research and who does it actually affect? So in terms of the retrofit policies in industry, enhancing the standards that we set and then enforcing those stricter standards for installation practices and material performance is a great way to ensure that we have longer term efficacy of these installation products. So making sure that it's done correctly and the materials themselves, they're obviously to a high standard and robust and resilient. This could be supported by having incentives for quality. So making sure that there's an incentive for best practice, an incentive for maintenance. Again, all of these things designed around making sure that those installation products perform to the highest degree of their potential for their entire product lifespan. There's room for research and development. So products at the minute installation products are light years ahead of where they were 50 years ago. Could they be light years ahead further in 50 years in the future? So hopefully the industry will continue to innovate, continue to create more durable insulation materials, better installation techniques, better fixing methods, simplify the maintenance of these materials, and just essentially get better and better. There's always room to improve. Data collection for both homeowners, large landlords, but also industry and beyond, by establishing a comprehensive data collection framework so that you can monitor the long-term performance of an installation, a retrofit, a product. You can then use that data to inform future decisions around policy. And finally, training and certification. So implementing training programs and certification requirements so that installers can ensure they're equipped with the necessary skills and necessary knowledge to do things correctly at the outset. And then also applying training and certification to the person who's responsible for that. So whether it's an occupant, to educate them on how to interact with insulation in their home, or whether it's estate teams, housing officers, so that they can problem solve or spot issues before they occur. All this will help to mitigate and offset any reduction in performance over the lifetime of that product. And again, just make sure that you're getting the most energy savings and the highest value out of those insulation materials. So the kind of last couple of slides here is thinking about what next. So the project's designed as a phase 1 evidence gathering exercise. So if it does roll into a phase 2 and there's more data gathered, how do we summarize our recommendations and what might a phase 2 perhaps look like? So the report itself highlights the lack of long-term data on the performance of retrofit in real-world conditions, with most existing studies focusing on short-term performance. They're using idealized lab conditions. It's not representative of real-world scenarios. This really limits the usefulness of the data that's out there currently, and it's also not comprehensive either. So to fill this gap, we need the opposite of that, essentially. We need long-term data from UK-based environments and UK real-world in-situ data. So this would ideally cover a range of the most common insulation types used in the UK in different representative regional contexts, so that we can get a set of data that we have real confidence is representative of the homes that are in the country, so we can write national policy against that. And gathering this data would allow us to do a couple of things. So if we had lots of data from naturally aged materials, we could develop a library of performance data for those products. So we could have a set of performance characteristics for insulation that is brand new, 10 years old, 20, 30, 40, perhaps insulation that's been affected by moisture, insulation affected by compression, insulation affected by vermin, all sorts of different ways that we could test and evaluate that. And secondly, applying those methods of thermographic surveys, visual surveys, borescope surveys, we can, if we did that over a larger cohort of homes, we can get a handle on the scale of the post-installation deterioration too. So if we look at a larger number of homes, we can see whether it, as I discussed before, is it just a lot of Christmas trees compressing a small area of insulation in the loft, or is it a lot of larger scale, bigger issues? Because that allows us to target the severity. Is it going to be point moisture issues in a home, or is it actually an overestimation of the total energy consumption of the home that's more relevant? Now, that's not without challenge or complexity. getting real world data means field tests or a complex extraction of materials. So when testing a real building, you're effectively characterizing a system, not an insulation product. So the bricks, the mortar, the plaster, the surface finishings, they'll all have deteriorated alongside the insulation product. So methods will have to be developed to isolate the role of the insulation against the other materials that are surrounding it. However, if we can successfully do that, we can do two very important things after that. So firstly, this will enable us to update our assumptions used in our models. These can be national scale models, where we look at projecting future domestic energy consumption, demand. We can use that for sizing of grid requirements in certain areas. If we think the performance of homes in certain locations is deteriorating faster than others, we can prioritize those for future energy demands. We can also use that library of aged performance to do granular risk assessments. So we can model individual homes, individual retrofit systems, insulation systems, and more accurately predict the risk of or the performance characteristics in the future and get ahead of those problems before they manifest. So all that, and the reason for doing all that, is that we can actually generate evidence-led policy on incredibly important topics. So future grid requirements and supply is one. We can target our retrofit delivery. And there's a host of other housing concerns that data on old insulation, aged insulation, would allow us to do. And so by helping to develop these kind of policies with a longer term outlook, we can be aware of and actually incorporate future challenges into those policy documents. And that just makes them more likely to be robust and ultimately more successful. So the deterioration of retrofit, please do. I've put the link. I don't know if the slides will be shared. I imagine they will be, but if you can Google it as well. The full DRIP report is on the government website. Hopefully that was interesting to everyone here. And I do welcome any questions that you have about the DRIP project. And thank you for your time today.
Thank you, Martin. I think that was indeed a very interesting presentation. I definitely found it interesting. I hope you all did as well.